Class 2, the solid state. Today we are going to study Introduction to Solids, Metallic Solids, Ionic Solids, bonding in metallic and ionic solids, and the phase diagram. What is a solid? Well, the solids contain definite shape, definite volume, highly incompressible. They are rigid. They are made of particles that are held closely by strong intermolecular forces, and they are in fixed positions. The use of diffraction from a crystal using X-ray allows us to study the structure and the different planes made by the particles in the space. The X-rays go through the crystalline solid and produces a pattern, and this pattern can be studied to establish the structure of the solid. What is a crystal lattice? When allowed to cool slowly, the particles in the liquid will arrange themselves to give the maximum attractive forces. So they minimize the energy. As a result, we get a crystalline solid. The structure of the crystalline solid is called crystal lattice, and they are made of a unit cell. The unit cell is the one that is repeated all over the crystal structure, but is the same one all the time. Unit cells are three-dimensional. They are repeated, as I told you before, all over to give the microscopic structure of the solid, and each particle is called lattice point. The lattice planes are planes connected by equal points in unit cells throughout the lattice. Here we have an example of cubic cell where we have in every corner we have an atom. Here you have the 7 unit cells that are possible according with the dimension of the width, length, and height, and the angles between these sides. The number of other particles in the number of other particles that are in contact with one of the particles is known as coordination number. For ions, it is the number of opposite charged ions that are in contact with it. The coordination number reflects the packing efficiency. If the percentage of the volume in the unit cell occupied by particle is very high, then the packing is more efficiently. In other words, the space in the cell is most occupied. There are two types of solids, the crystalline and the amorphous. Crystalline solids are building constituents arranged themselves in regular manner throughout the entire three-dimensional network. A crystalline lattice is a solid figure which has a definite geometrical shape with flat faces and sharp edges. They are incompressible. They have definite sharp melting points. They have anisotropy. It means that the properties in one direction are different from the properties in the other direction. They have definite geometry, and they give an X-ray diffraction band. For example, we have sodium chloride, cesium chloride, etc. The amorphous solids are shapeless. They have no regular arrangement. They are considered supercooled liquids. They have no sharp melting points. They are isotropic. It means that the properties are the same in one or other directions. No definite geometrical shape. Do not give X-ray diffraction bands. Example, glass, rubber, plastic. The types of crystal could be ionic crystals, covalent crystal, molecular crystal, or metallic crystal. The ionic crystals are made of positive and negative ions. They are very hard and brittle. They have high melting points. They are poor conductor of electricity, but in melting point, in melting state, they are good conductors. The packing of the spheres depends on the presence of charged species. The difference in the size of anions and cations. We have two types, AB types and AB2 types. The covalent crystals have a lattice points occupied by neutral atoms, and they are united by covalent bonds. They are hard solids. The melting points are very high, but they are poor conductors of electricity. Two examples are diamond and graphite. The molecular crystals are neutral molecules that are joined by van der Waals forces. They are very soft solids, low melting points, and they are poor conductors of electricity. The metallic crystals are made of a red, made of positive metal ions surrounded by a Z of mobile electrons. These are the valence electrons. They are soft to hard. They have high tensile strength. They are good conductors of electricity because of this sea of mobile electrons. They are malleable and ductile. The bonding electrons in the metal remain delocalized, delocalized over the entire crystal, and they have very high density. The types of cubic crystal can be simple or primitive type, body center, face center, or end face center. Here you have the primitive one. It has in every edge you have an atom, and in the body center you have also an atom in the center. You have the face center where you have in every face an atom, and the end face center that has only atoms in the upper and lower part of the cell. Here you can see the simple cubic, the body center cubic, and the face center cubic cells. The number of atoms per unit cells can be calculated. For example, in a simple cubic, you have one atom in every corner, but every atom is one eighth of the atom is in this cell. So if you have 8 atoms and every one provides only 1/8, you have at all one atom belongs to this cell. In the body center, you have the same thing, but beside that, you have another atom in the center that belongs to this cell. So you have 2 atoms per cell. In the qubit cell unit, in the face center qubit unit cell, you have 8 atoms in every corner that provide 1/8 of each, and you have 6 atoms that provides 1/2 to every cell. So you have at all 4 atoms in this type of cell. In general, you have the simple qubit cell has a coordination number, that is the number of atoms that surround any one of them, that it has every edge of the cell is 2 times the radius of the atom, and the packing efficiency is 52%, is the part of the cell that is occupied by atoms. In the body center cubic, you have 2 atoms in every cell, and the coordination number is 8. This is the edge, how you can calculate the edge of the cell, and 60% of the cell is occupied by atoms. In the face center cubic, you have 4 atoms per cell. The coordination number is 12. This is the way you can calculate the every edge length, and the cell is occupied by 74% of atoms. Here you have an example of how to calculate the number of atoms in a simple qubit cell. You can stop the video at any time and you can see the calculation. Here you have for the body center cubic, and here you have for the face center cubic. As I told you before, you can stop the video at any time and you can see how to make the calculations. Let's see an example of calculating the density of a crystal structure. In this case, we are talking about aluminum that crystallizes in a face center qubit unit cell, and the radius of an aluminum atom is 143 picometer. You have to calculate the density in grams per cubic centimeter. Then what is given? The radius, the structure of the cell, and what you have to find? The density. Then what you have to do? Let's see. First of all, you have to begin calculating the mass of the unit cell. How can you do that? Well, density is mass over volume, the mass of the unit cell. How you calculate this? Oh, the mass of one atom is 26.98 grams per mole. Is a molar, the atomic mass of aluminum. Then if you multiply by the Avogadro's number, you can calculate the mass of one atom. And if you know that the type of cell that contains 4 atoms, you can say then that 4 times the grams per atom give you the mass of the cell. In other hands, you have to calculate the volume. If you know the formula to calculate the one side, and you know that the radius of the atom is 143 picometer, and you convert this into meters, and later you calculate the volume, raising this to the cubic, and after that you convert into centimeters, you calculate the volume of the cell that is here. Then you divide the mass over the volume and it gives you 271 grams per cubic centimeter. Of course, the units are correct. Grams per cubic centimeter. The magnitude is reasonable because it's greater than 1. That is what is expected for metals. But it still is not so high because the density of aluminum is very low. Here you have an exercise where you can get some practice. You can stop the video and do this exercise in your notebook. Then we have the crystalline solids that could be molecular, ionic, or atomic. The molecular are made are